Okay, in this video we will be going over resonance in RLC circuits. And as a brief overview before we get into things, an RLC circuit consists of a resistor, an inductor, and a capacitor connected in series across a voltage supply. And this circuit can exhibit the property of resonance at a specific frequency or the resonant frequency. We'll explain a little bit more about that later. Right now we will first discuss how each of these individual components of an RLC circuit works on its own in a circuit. Okay, starting with the inductor. So here we have an inductor in series with an AC voltage source. And when we have this, a sinusoidal voltage given by this green line is applied to the inductor. However, this voltage leads the current by 1/4 of a cycle. And this is because inductors oppose change in current, acting as an effective resistor to the alternating current. Inductive reactance, or X sub L, measures the opposition of current flow and is measured in ohms, just like resistance. So the inductive reactance and the inductance, as you can guess, are proportional to one another, meaning that as induction increases, so does the resistance to change. And inductive reactance also increases as the frequency increases, shown by this graph. And this is because the greater the frequency means the greater the change in current, which creates more opposition from the inductor. Now with the capacitor. So as the voltage across the capacitor and current are both graphed as functions of time in this graph here, we can see that the current starts at 0 when the capacitor is fully charged. And as the cycle goes on, the voltage, again shown by this green line, lags behind the current by 1/4 of a cycle. So this is the opposite of what we saw on the previous slide. The capacitor is able to change the current, stopping it completely when it is fully charged. And so the larger the capacitor, the greater the charge it can store, and the greater the current that can flow. The greater the frequency, over here in this graph, you can see the greater the frequency, the less time there is to fully charge the capacitor, so it impedes current less. So the lower the capacitive reactance, and there's a greater frequency. So capacitive reactance is inversely proportional to both capacitance and frequency. Now with the resistor in series with the AC voltage source, the current and the voltage are exactly in phase with each other, unlike with the capacitor and the inductor. So now when we combine the resistor, the capacitor, and the inductor all into one circuit, even though all three of these impede current when they are alone in an AC circuit, when combined, these resistances can't just add together nicely. So what we get instead is what's called impedance, known by Z. So that's the combined effect of the resistor, the capacitive reactance, and the inductive reactance. And here below is the equation for it. Again, can't just add them. So that's how we will solve for impedance. And the inductor and the capacitor, as we saw a little bit before, they act in opposite ways. So this allows them to at least partially cancel out each other's effects, if not fully. And here on this side we can see if we were to superimpose these two graphs, we could tell that they could at least partially cancel each other out. Again, depending on the magnitudes of the graphs, we might be able to fully cancel out the effects of both of these reactances. And when it comes to resonance, we actually will be able to cancel out the effects of these two different reactances. So as mentioned before, the reactances vary with frequency. And when the inductive reactance, when we have a high frequency, the inductive reactance is large. When we have a high frequency, the capacitive reactance is smaller. But at this intermediate frequency, the reactances will equal each other and will cancel out. So, equal each other. And when this happens, we have reached a resonant frequency and we have resonance. So, at this time, the only opposition to the flow of current is from the resistor. So if we take a look at this graph below, we can see that since these are the same, this will be equal to 0. The only thing affecting the current is the resistor, and current will be at its maximum value when resonance is taking place. And if we remember back to our definition of impedance, it was the combined effect of the resistor and capacitive and inductive reactance. So since those reactances are equal to 0 when combined, the only thing affecting impedance is now the resistance. So Z is equal to R. Impedance is equal to resistance. Alright, and so we can get the equation for F0, or the resonant frequency, by starting with this, inductive and capacitive reactances equaling each other. This is the same thing. We're just now substituting in the equations for the two reactances as we saw in the previous slides, and we solve for F0 to get this formula. So if you're given a problem and you need to solve for the resonant frequency, this is probably where you will turn to. And as far as applications of resonance in RLC circuits goes, since resonance only occurs at a particular frequency, this can be used in radios and televisions, for example, to filter and tune while avoiding unwanted oscillations that can cause signal distortion and unwanted noise. So, pretty cool application, and hopefully this video helps you understand how that all works.